Okay, so good morning again. Nice to have you here. And we will continue today and also coming to an end of our course during this day with drawing behavior. It's a bit loud today, huh? Better? And you see here our dryer installation in Hohenheim, some of our precision dryers. And we will work today with drying fundamentals, but before we go into fundamentals, I will show you at least 4 slides of drying in practice to show you why we need those fundamentals. This here is the most simple dryer, just a box and a perforated floor, and the drying material is put inside and we are blowing here the air through this bulk of material for drying. And you can imagine that the dry air is coming in here on the bottom floor here and then takes up water more and more and more and is escaping on top of it. Morning. And this is as those dryers might look in practice. This is Thailand here, and we are drying here longan. In those boxes here, we have here several boxes, one box after the other, an array of boxes also on the other side. And you see here a fan, and in front of the fan there is an air heater with gas. So by gas, the air is heated and then blown into the dryer and penetrating the material, the bulk, and escaping on top. You see all the gas bottles here behind. So those dryers are fired by gas. And there are no heat exchangers. So it's a direct effluent gas from gas burning. This is cleaner, of course, than wood or oil heating systems, but I'm not sure if this is the best way to work without heat exchanger. We still need some research if there are some residues when we burn gas directly for drying. Okay, but this was only a side comment. Here in the next slide we see here the bulk before drying, and we have the same moisture content here from the bottom to the top here. Of course, there are varieties. If you bring inside material, it's not a uniform moisture content, but we assume it is uniform. And then we have here drying on the bottom here. The drying zone here is on the bottom. Here material is drying, and then the air is already saturated here and cannot take more moisture. We have now 100% saturation. And also the air is cooling down here by taking water. We have learned this by psychrometrics. So by evaporation of water, the air is cooling down. And this is just stagnating. You see the moisture content here has been dropping here, down here, and here it's still the original moisture content. And it's even worse. We have now here warm air and saturated air. If we have heated it, maybe we started with 50 degrees centigrade here, then it cooled down maybe to 40 by evaporative cooling, and then we have here 40 degrees centigrade and 100%. This is optimum for microbial growth. It's just an incubator. Okay, then the product might be dried here at the bottom, maybe even over dried, because we have applied 50 degrees, so we go for grain below 14%. It's an over drying, so we can affect the quality by over drying, and also if we have the product dried too much, we cannot sell this water. We are selling less mass. It's not a good idea to sell grain with a moisture content of 5%, because you can sell it at 11 or at 14 even, and making more money from it. Okay, this is not a good situation, over drying. Now we have here the drying zone, and you see moisture content went down here, and here we have the drying, and we have still the initial moisture content on the rest. And finally, at the end, the drying zone is coming out above and the entire bulk is dried. Okay. So, and those are now real curves here over time. Yeah, we have here the moisture content over time. You see here the first 40 centimeters here. Moisture content goes down in this layer. The next layer here is waiting for drying, then going down, and then next and next and next are following. Okay, and here the air velocity is very decisive. The more airflow we have, the more air volume, yeah, so the larger is the drying zone and the less is the zone which is waiting for drying. And therefore, airflow is very important for bulk drying, but you will see later on, not so much for thin layer drying. So, and here we have now the fundamentals of the drying process. We have here a kernel here in the center. We have here a certain air condition which is going in here, a temperature here, certain temperature and a certain absolute humidity of the air. X is blown over the kernel here. And at the outlet, we have a certain temperature at the outlet and also a certain absolute moisture content at the outlet at a constant enthalpy. Yeah? So what would you say about the temperature in contrast T out, in contrast to T in? What about T out? Same temperature or different temperature? Lower. Lower temperature here for T out. And for X, same X as X in or different one? X is lower? Upper. X is higher. So the absolute moisture content here is rising. Okay, what are the mechanisms? You see here the hot air here, yeah, is passing by here. Yeah, first hotter and then cooling down. We have seen here, and the heat is transferred to the center of the kernel. So what is going on here at the surface? Yeah, so the heat goes from the air here to the surface here. It's a matter of the temperature gradient. Yeah, if there is a high gradient, then there is more air going, more heat going from the air to the surface. It's a matter of heat convection. Yeah, so heat is transferred by convection here to the surface and the air velocity. If there is a higher air velocity, then this convection here is enforced. Okay. What about then here from the surface to the interior? It's again a function of the temperature gradient. Yeah, so a high gradient push the temperature inside the kernel and also the heat capacity of the material. If there is a high heat capacity, it takes a long time until the heat is penetrating here, this grain, and also heat conductance. The heat has to be conducted inside the grain, yeah, inside. What about the mass transfer here on the other side? What about the water? So we start here with the surface here. Yeah, air is coming to the surface, and this is then a matter of saturation deficit. Yeah, the higher the saturation deficit, the more water can escape here from the surface and go into the air. And a matter of air velocity. Yeah, air velocity here is enforcing here this process. So then from, now we go the other way around. Yeah, we go here from the interior here. We have the water inside here, and first the water has to go from inside here to the surface. And here the diffusivity is a driving force. The diffusivity of water in the kernel. And this is a function of temperature. the higher the temperature, the higher is this diffusivity. So we have two reasons why temperature is so important for drying. So we are increasing here the saturation deficit, which we have learned, and we are increasing the diffusivity inside the kernel, and so the water can penetrate quicker here to the surface. Okay, those are the principles. And now you see here the precision dryer in Hohenheim. Here in this cupboard here, we have a tray on balances here, and that means we can record the mass of the drying material inside, and we are pushing air through this tray, and this air is conditioned in all this equipment here behind the dryer. Here we have a through flow dryer. We are pushing the air through the material from bottom to the top. And here we have an overflow dryer, so the air is pushed over the material from right to left in this picture, as we are doing this in our tunnel dryer. You remember the solar tunnel dryer? There the airflow is above the material. Here the airflow is through the material. Yeah, you see it a bit from the other side. Yeah, here better the overflow dryer. You see just here a weight inside for calibrating the dryer. There is also a balance here, this platform. And we can switch the airflow either to through flow or to overflow. Again, you see here the other side of the balance. And you see also a difference. Yeah, here is through flow drying. We have here cubes of material, let it be papaya cubes, what we are dealing with today. And you see here a CFD simulation, so an airflow simulation by software. And you see the red arrows indicate a high velocity, and the blue one a lower one, and you see that we are speeding up here the air in those slots. There is a high velocity, increasing the heat transfer from the air to the product. In contrast, we have here the overflow. Air is coming from the left, and you see it's going higher up, and the air here in between the cubes is quite slow. So there is then a lower mass and heat transfer, and you see it also in the drying rate, how quick is drying in kilogram of water loss per kilogram of dry matter an hour. And you see here the curve above is the through flow dryer, where we have a higher drying velocity than in the overflow dryer. Not so big the difference, but it is there, and therefore we have to make investigations with both types of drying. Okay, a little bit to the function of this precision dryer, because it also has much to do with psychrometrics. You see here our dryer chambers here, through flow dryer and overflow dryer, and you see a bypass system. Either we can go here to through flow, or we can go here to overflow. And here is the inlet of the air. You see 3 intakes. They have intake nozzles, and by those intake nozzles we are measuring the air velocity. By the pressure drop at those nozzles, you can measure very accurately the airflow, and if you need a high airflow, you have to use a big nozzle, and if you need a low airflow, you take a small nozzle. There is an air filter to bring out the dust, a ventilator, and then going to our air conditioning system. And this is now a quite innovative thing. We have here a packed bed with particles, and we are spraying water on these particles. And then we bring the air through, so that the air is to 100% saturated here after passing this packed bed. And the water temperature we can adjust. So we can cool the water. You see here a cooling system. We can heat the water. And the air is here leaving the system with 100% saturation and the temperature of the water, because there was enough time here to penetrate here the packed bed, to get saturated and to get exactly the temperature of the water. And now we just adjust the dew point temperature of the water, or other way around, the temperature of the water will be the dew point temperature of our air. In that case, dew point temperature and wet bulb temperature is the same, saturated and having the temperature of the water bath. And then we go immediately here to the heating system. Otherwise, water will condensate at the walls. Even the walls here are heated so that no water can condensate. So after leaving the packed bed, the air is immediately heated and then brought to the dryers, and just below the drays or before the drays there is additional heating system for fine adjustment. So we are heating maybe 5 degrees below the toucher temperature and then heating the rest here just very close to the drying material. Okay, why so much talking about? Because it's a repetition of psychrometrics. We see here our ambient air, what's happening in our packed bed. So we are moistening, so we go down, but we are also going to the temperature of the water bath, which is in this example here, so I would say 17, here is 15, 16, 17, a bit more, 18 degrees centigrade. Okay, now we have here our adjusted absolute moisture content, because this temperature is corresponding here with the absolute moisture content of the air. So we are defining the absolute moisture content by the dew point temperature. The two are combined directly. So if we have, for example, here a dew point temperature of 20 degrees, then we have here 15 gram of water per kilogram of dried air. You see, this is directly correlated. You always can go from this point here up and read here the absolute moisture content. So this is a perfect method to adjust the absolute moisture content of the air. So, and then we are preheating here, and then the rest is the precise heating to, in this case, 45 degrees centigrade for drying tests. So, what do we then measure? Example here, the lemon balms, the Melissa officinalis. We have here the drying time here, the moisture content. So the mass is converted into moisture content, and then we have here a typical drying curve. Typical drying curve here, going down over time. In this case, it's 40 degrees centigrade, 0.2 meter per second air velocity, and here dew point temperature 13 degrees centigrade, corresponding with a certain absolute humidity of the air. So we have adjusted in this example 40 degrees centigrade. This is this line, and we also measured the temperature in the product. This is this dotted line, and you see coming from the storage room here 21, 22 degrees centigrade, and then the temperature is rising, the product is heating up, and then remaining here on this temperature and slowly reaching the temperature of the air. Why is this the case, this behavior, this temperature behavior? Why don't we just heat up and then be on 40 degrees in the leaves? Psychrometrics. What would you say? Why is the leaf cool down during heating? Like the psychrometer, like the wet bulb. So we are remaining here around wet bulb temperature quite long, because a lot of water is now evaporating from the leaves. And therefore the leaves are cooling down themselves. That's the reason. And therefore, for some products, you can apply quite high drying temperatures at the beginning because the leaves are cooling down themselves. Yeah? This is used in belt dryers where you can adjust different temperatures in the belts, so then you can run the first belt on a higher temperature because the material has a self-cooling effect. But you also have to measure quality. Yeah, now we are testing different temperatures, yeah, and we have a look on the quality. Here it's again Melissa, and you see here the leaves here from top. You see some of those spheres or bulbs. Here are the essential oils. That's what we want to have, essential oils from those plants like peppermint, sage, lavandula. And this is the leaf from the downside here. And you see it even better here, those nice bulbs here. We have more of them on the downside than on the upper side in Melissa. And they might be damaged by high temperature. And what we see here is drying time and the essential oil content of the product. And for different temperatures, here 30, you see nothing, there is a certain loss, but not tremendously. And then the losses are rising, This is 45, and then we are coming to 60, 70, until 90, and you see we are pushing out all the oils. So we have to make these experiments to see how high can we go with drying temperature. I would say, okay, 45 might be acceptable. Depends on the farmer and the buyer, how much oil is expected in the material. And this is now an example for sage, Salvia officinalis, the oil reduction. This is now the reduction of oil over the moisture content. So we start from the right, from a higher moisture content, fresh material brought in. We are in the middle of drying. It came in with 70% moisture content, and we have here 90 degrees centigrade and here 60. And you see, if we apply 90, it is lasting until we have the losses. The losses are here occurring at the end of drying. Losses are going up. If we have 60, there is nothing happening until coming here to 10%, and then we are facing those losses. So if we now could stop here drying at 10%, what we need, this is target moisture content, we are fine off. We could apply a high temperature here without facing losses. Of course, we have to know this time. We have to know exactly when to stop drying. If we have over drying, we are spoiling the material. So, and this shows here this problem. If we dry here with this 60 degrees centigrade and this is now here the drying temperature. If we apply 30, 45, 60 up to 90 degrees centigrade and we dry to the target moisture content of 11%, this is the one for sage, then you see, okay, you can go to 60, but if you apply 75 degrees centigrade, you are facing losses. And if you dry even to equilibrium moisture content, drying to the end until no more water is escaping, then you see you have losses already here at 50 and at 60 and so on. So if you have a high sophisticated dryer, such a belt dryer, then you can stop drying at 11%. If you have a batch dryer, packing the material in such a box and having a high bulk, then you are over drying the bottom layer until you are drying the top layer of the material. Okay, but it's also a question of color in those plants. It depends what you define as quality. In medicinal plants, of course, the active ingredients like essential oils, but also the color. because the customer is buying the material maybe even in open bags or plastic bags in the supermarket and looks for color. And color, yeah, is something you can discuss about. There should be a measurement system for color, and there are some. And a very famous one is the LAB scale, where L means the lightness, and A means here a value between green and red, and B means a value between blue and yellow. And you see, if you come from the center outside, the color is more and more intensive. Yeah, in the middle you have the gray value of a color. And the axis which is now penetrating the screen shows the L value. Can be black or can be white as an extreme. Here we are in the middle. Do you know about this LAB scale, or do you know about color measurement? Okay, yeah, then I can speed up. So we are using here the U angle here. Yeah, this is this angle to show where we are on this circle, and the saturation C, yeah, is the Pythagoras here, yeah, that shows you the distance from the center, which means the saturation of the color. So, and this is now an example again for Melissa. We applied here different temperatures. The white one is the fresh material before drying, and then we have 30 to 90 degrees centigrade, and you see the L value is decreasing, and on the right hand you also see how it looks visually. Yeah, we have here with 30 degrees centigrade this nice green color, and if we increase temperature it's really going down to brown. Okay, it's a bit hard to you see it in the A and B values, but it's always nice to have here the U angle, yeah, combining the two, A and B, and then you see really almost linearly we hear the color is going down, yeah. So getting more brownish, yeah. And saturation is going down, and here this is maybe the most best indicator here, the A here, this goes from green to red, from the green area to the red area. Yeah, this is color, and color alone is a quality parameter, but in this case the color change also indicates the chain here of rosmarinic acid. Here in Melissa it's not only the essential oil, it's also the amount of rosmarinic acid. And these compounds, when they are oxidized, they change the color here from green to brown. This is showing the oxidation of rosmarinic acids. That means here the U angle, this is this one here, and the rosmarinic acid equivalents here, they are directly correlated. Yeah? If U is going down, if it's more and more reddish or brownish here, then we are also losing the rosmarinic acid. Okay, just to show you what we measure when we do fundamental research. Yeah, and then you see different drying lines here, different moisture content lines for Melissa, chamomile, and valeriana, Valeriana officinalis. This here is a herb, this here is flowers, and valerian are roots. So we picked these examples to show different organs of plants which are dried, and you see, okay, there is a certain difference. So you have to make experiments for each material you are interested in. So now we are coming to those drying curves. We can express this in moisture content wet base. The ones in everyday life is spread. The mass of water related to the total mass here, where the mass of water is a function of time. Water is going out. And we have it here on both sides here. And therefore, the basis is not constant. And we have such an S curve going down. If we present the drying curve in dry base here, we have here constant basis. This is a dry matter, and here the mass of water is a function of time, and we have here this drying curve going down. And now there is a convention to express those drying curves in the so-called moisture ratio. Now very important, also for our practical. This is a definition of the moisture ratio, the moisture content, dry base, as a function of time, minus the moisture content at equilibrium. You remember absorption. And there is then an equilibrium with a drying air. Keep in mind, this is now, can be now very hot, yeah, 50, 60 degrees centigrade. So the relative humidity will be very low, yeah, and therefore also the moisture content of the product can be far below the target moisture content, which you need for safe storage. Okay. So then we have here the moisture content initially, how did it come in drying, and again we have here the moisture content at equilibrium after long drying. Okay, so what will happen here at the very beginning? Let's see at time t0, at time 0. What is the value of the moisture ratio at time 0? It's 1. And this is also here the meaning of the moisture ratio, to standardize drying curves, to bring them all to 1 at the beginning. Why 1? Okay, because then moisture content is moisture content initially. MC ini, and then both terms are the same, and the value is 1. Yeah, what about long drying? Reaching equilibrium. What is the value when we reach equilibrium? After a long time? 0. I agree. It's 0 because then MC from T is here MC equilibrium. And then this is 0 and the whole term will be 0. This is the idea of the moisture ratio. Yeah? Standardizing drying curves going from 1 to 0. And then the only difference is how they move. Yeah? How this line is shaped. Okay. Here we have, again here, our moisture ratio. I have explained it already here. And we can now also solve this moisture ratio here to the moisture content which we have at a certain time. Yeah, just solving here for moisture content at time t. Then we have this shape of the equation. Yeah, that means if we know here the moisture ratio, given in publications, because we are publishing then our drying curves in this form. It's like a wrapping. Yeah, so we wrap our materials very condensed here and present it here as moisture ratio. If you know moisture ratio here and the initial moisture content and the equilibrium, then you also can calculate the real moisture content of your product. Yeah, not anything between 1 and 0, but then let it be 14, 15, whatsoever percent humidity. We will do this later on in the practical. And again, for these drying curves, there are models in the scientific world, a lot of models. We are just brought here as one selection here with very frequently used ones. The simplest one here is the Newton model here. Yeah, moisture ratio is just e power minus a coefficient C1 times drying time T. Only one coefficient. Very, very simple, just an E function going down here. The next more complicated one is Page model. Here we have two coefficients, yeah, minus C1 times T power C2. Fine, and so on and so on. And always we try to select the most simple one. if you add coefficients, you can everything. You can make polynomials, yeah, with a right number of terms. You can approximate everything, but this has no meaning at the end. Yeah, here we still have this nice exponential function, just with a different arrangement of the coefficients. So Newton or Page are fitting in many cases. So by the way, Page, that was a model a student did as his MSc work and is now so famous and now so frequently cited. Okay. So I showed now the moisture ratio here as a Newton model here, yeah, just E power a constant K times T, yeah, and then you can solve it for T. You just can solve the equation for T, yeah, and then you have here the moisture ratio for a certain time here. But a certain, if you want to see here the drying time you need, yeah, you look here for the moisture ratio, which is reflecting here your target moisture content. 14% for cereals, for example, 11% for sage, yeah. And then you put here the moisture ratio here, the target moisture ratio, and then you can calculate here the drying time you need. And if you set here instead of the moisture ratio here this term here, then you have the moisture content target, the one you need, minus the moisture content equilibrium over moisture content initially and minus moisture content equilibrium. So you know, of course, the moisture content initially, how you bring it in from the field. You know, hopefully, your moisture content target from the sorption isotherm, equaling the 0.6 water activity, remember, or 60% relative humidity in the pore volume. Then you can see the target moisture content, and what you need to know still is the equilibrium moisture content at your drying condition. So at, for example, 60 degrees centigrade. And therefore we need sorption isotherms not only in temperatures which we use for storage, as we have seen yesterday, so 20, 30 degree, maybe 10 if you are cooling. We also need the sorption isotherms for high temperatures, which we apply for drying. And many people forget this. Many people, when they do sorption isotherms, just measure, so in this range, 10 to 30 degree. And you cannot extrapolate to higher temperatures. So therefore, we measure also sorption isotherms at high temperature, 60, 70, and then we can interpolate in the whole range, from, let's say, 20 to 70 by those models which we have seen yesterday. So now the impact of these different drying parameters. First drying parameter, air velocity. You see here drying curves over time, 4 different air velocities in our precision dryer, 0.2, 0.4, 0.6. It's a threefold air velocity, and you see there is no significant difference in drying curves. And also if we then look for the drying time, the time we need to reach the target moisture content for 0.2, 0.4, 0.6 meter per second, you see, okay, it's a horizontal line, no influence. And now this is contradicting what I told you at the beginning. In bulk drying, of course, there is a tremendous influence to airflow because of this saturation problem. In fundamentals, by purpose, we are working with single layers, as thin as possible. Because in the layer, the air conditions are changed by drying. And therefore, we try to have the single layer that we don't have this cooling effect of drying, of this evaporation heat. Yeah, that we really have from the inlet to the outlet the same air condition. Okay, and in this condition here between 0.2 and 0.6, there is not a big difference. If you go below 0.2, then it starts to change, because then you have also laminar flow, yeah, and you have no convection around the product, and then you also see it here in thin layer drying. But this is not the real drying condition. Yeah, you look in dryers that you have at least air velocity of 0.1 to avoid this laminar flow in your dryers. What about the relative humidity of air? We have here the moisture content here, again over time for 30, 40, 50 to 70 even, 70% relative humidity, and you see there is a difference, okay? So for 30%, the drier air, we have a quicker drying. But what is even more important, at the end here, we have here different final moisture contents. You cannot reach a low moisture content with 70% relative humidity. It's again a matter of equilibrium. This is higher than if you use dry relative humidity of 30%. And if you draw this line here, yeah, to reach target moisture content, you see you just can reach it with 60%. Because this is here our safe storage condition here, relative humidity of 60%. And then it goes up, yeah, because you cannot longer reach it. What about temperature? Here we see the curves for 30, 40, 50 to 90 degrees centigrade, and you see the influence is tremendous. If we go here, looking for the drying time we need, at 30 to 90, it's going down again kind of exponentially. Okay, so this is really the driving force in drying, the temperature. We have seen two effects: increasing the saturation deficit, reducing the equilibrium moisture content, and increasing the diffusivity of the product. All those three effects are really forcing drying. Yeah, now you could claim, okay, but if I have to apply a higher drying temperature, I need more energy. I would say no. I would say yes when you tell me I need more power, more heating power. Why that? Yeah. So the thermal power requirement here, this is directly increasing with temperature. If I rise temperature with 5, 10, 15, 20 degrees centigrade, I need more heating power in the same range. But the drying time is decreasing progressively, yeah, in the power of 3. Yeah, and therefore here, if we increase the temperature here, the drying time is going down, the power I need is going up, but the energy is power times time, and therefore at the end here, the relative energy content requirement we have is decreasing even. I need less energy when I apply a higher drying temperature, because I am shortening the drying time. Okay, here you see an empirical equation for the drying time for Melissa, so it's a function of temperature power 3, what I told you, yeah? This is a function of power 3. Yeah, this is a reason why we try to go as high as possible, and as high as possible means until harming the quality. Therefore, we always have to look what is the quality criteria of the product and how high can I go with drying temperature. Okay, so now we come to prepare our practical already. I have here sorption isotherms, and I have this for papaya. This is from the papers I also have uploaded to the platform, and there is some paper of the publications also for you. And you see here 2 sorption isotherms, one for 20, one for 60. Why? The one for 20 degree centigrade is the one which is responsible for storage. We assume products are stored at 20 degrees centigrade. And then we have to look here for the water activity of 0.6. This is this line here. And then we go to the left and then we see, yeah, for this product, a moisture content, wet base of 25% is sufficient. So you could store papaya at 25% moisture content. Yeah, I can also tell you in this study we also applied osmotic pre-drying, so you even can add some sugar in the product by osmotic pre-drying, so some sugar is absorbed from the product. And you see here the moisture content, safe moisture content for storage is quite high, 25. So, but what will happen when we dry? We apply here 60 degrees centigrade. So this line is now the responsible one to calculate the equilibrium moisture content. If I apply here 60 degrees centigrade, I am on this line. And when I take ambient air and heat it up to 60 degrees centigrade, it will not be longer here 0.6. Yeah, it was maybe 20 degrees centigrade and 60%, but by heating, the new relative humidity is now here around 8%. And if we now go here to our sorption isotherm, we see that the equilibrium moisture content here is below 10, yeah, maybe 11% moisture content. That means the drying is going towards an equilibrium moisture content of 11, not 11, it's below 10, let it be 8% moisture content. And here on the right, we see now the drying curve. And you see it's going down here and is reaching here our target moisture content, which is 25. And if I don't stop it here after this, let's say 10 something hours, drying will continue and will finally reach here this equilibrium, yeah, this 8%. Over-dried, hard. Yeah, even for the consumer, this is now a really bone-dry product here, hard to chew, whereas here the 25 is really a soft product, yeah, pleasant to chew. And if you go here until equilibrium, yeah, you will not only over-dry, you also will lose time and money, yeah. This is also then blocking the dryer, the capacity of the dryer will be lower, and you are heating all the air which you are blowing through, so it's a tremendous energy loss, yeah. So there is a very good reason here to know this point, to know the time here, and to stop the drying process at the right time. And this we will do in our practical, yeah, based on those publications. And you find here on a very close space in this publication what we need. We have here the model here, yeah, the Newton model here, the moisture ratio, E function, e power minus k times t. And we also can find here the k value. This is now the k value which goes in this equation. And the interesting thing is it's a function of temperature, absolute humidity, and air velocity. In our experiments, we have varied all these parameters. Variation of T, variation of air velocity, variation of absolute humidity of the air, and the combinations. You can imagine, I don't know, 150 experiments with the replications, and we have been able to wrap all this in such a small equation. It's now everything in, and you can see you can vary now T, you can vary X, you can vary phi, you can interpolate for all the conditions you like with this equation. And you have maybe in mind that you also now need here the sorption isotherm, and this is given here. This is a sorption isotherm. This was published in a first paper, and then later on in a second paper, the drying results where the model is related here on this sorption isotherm, which has been established in the first paper. And this is when I write the Halsey model here, this one. And you see we have 3 parameters. This one is given as a figure already. This is a parameter, and this in the exponent is a parameter, and we have T. Yeah, and here we have the equilibrium moisture content on the left side, and we have our water activity or relative humidity of the air on the right side of the equation. So we have already converted the equation, and we will use this in our practical. Yeah, this model of Newton here with these K values here. And when we now want to make real drying curves from the moisture ratio curve, I have shown you this form of the equation. Then we need here our moisture ratio, which is given by this Newton model, and you need the equilibrium moisture content, which is given by this Halsey model. So we have everything at hand, what we need, yeah, to make exactly here these nice curves ourselves for the conditions we would like to have. Yeah, so this is the moisture ratio, moisture content at target here. We take the sorption isotherm, we put inside here the storage temperature we like to have. If we know, oh, my store has 30 degrees centigrade, then I put here 30. And I put here the target water activity. Do I want to have 0.6 or 0.7? Or for a certain customer, it requires even 0.5. Yeah, I can put it here, and I can calculate here my target moisture content. And then here on the right hand here, we can calculate here the drying time T, which we need, yeah, to meet this target moisture content here. Okay, so that means we would be prepared for our practical. Do you have questions so far? Yeah. Yeah. The time? This one is ours, yeah? Unit in minutes or in days. Yeah, you just have you have to fill in your equations with this time, yeah, because you have coefficients, and the coefficients are really calculated on the units which we have used. But later on, if you come out here with 10 hours, you easily convert this in 0.5 days. Or 600 minutes, yeah? Yeah. You have to stick to the units, to those units. Time in hour, temperature in degrees centigrade. Look here, be cautious. Some are in gram per kilogram, some are in kilogram per kilogram. Very strictly, and here air velocity meter per second. It's very decisive. The coefficients are only valid for these units. Yesterday we had also this coffee paper, thank you to Mercedes, who uploaded to the forum. And also there, the coefficients they offer there are only valuable for their equations, also in the sequence. That does not mean that A is C1 and B is C2 and C is C3. It can be changed. And I first assumed that this is a mistake, that we just have to change the sequence of the coefficients. No. The problem is that they are applying a wrong model for the Chung-Post equation. I checked it and they solved it for moisture content, but not right. You cannot present it in the way they do with this A minus something. That never can happen, that the coefficient is such alone in the equation. So I wrote to the author already. Let's wait for the result. I seldom see that authors are really answering. Let's hope. You also are invited to write him. Yeah. Therefore, the addresses of the authors for one author, for the corresponding author, is always giving in the publication the email address. So, okay, send an email and let's wait if he is reacting. Okay. So then there is only one question, where is our coffee? And I think it's 10 o'clock, and when we are lucky, the coffee is prepared for us outside. Thank you. they still have to sign, huh? Okay. Mhm. Okay. Some are still missing, but maybe I can give you some general information about our practical. Our practical has here now several templates available, and it does not mean that we have to do all of them today. But the first one here is for making moisture ratio curves, and the second one to make real moisture content curves from it. And then we can proceed, and we can then here calculate the time which we need for drying to reach the moisture content, the target moisture content. And the other ones here maybe, if you'd like to continue for your own, we can have a look inside later on. Okay, I have prepared here this spreadsheet, and you also can click inside here and see the objective of this spreadsheet, but I can explain it, of course, for you now. You see here the scheme is drying time, and here the moisture ratio, and I have prepared here how many? Four columns here. And the idea is that we look at this drying curve for different parameters. What happens when we vary temperature or absolute humidity or air velocity, and it's based on the equations from the two papers we have seen already. And you see I have put here the units by purpose. That was your question. Those equations only work with hours in this case for this equation, and here this x is gram per kilogram and the air velocity is meter per second. Okay, so the first column just takes the parameters as in the publication. So example for 60 degrees centigrade, here 10 gram per kilogram absolute moisture content, and here 0.2 meter per second air velocity. And then I introduced here a line for the relative humidity. Yeah, very nice to know which is the relative humidity of this air, of this drying air. Yeah, going down from originally 20, going down to 8 in this example. And to calculate here the relative humidity, I gave you here these gray equations from thermodynamics. Yeah, we have learned that the relative humidity is the ratio of the vapor pressure over the saturation vapor pressure. And the saturation vapor pressure is a function of temperature, here thetans. You remember this equation of thetans. We just have here the temperature, 2 times the temperature, and then we have here our saturation pressure. And then we need an equation to calculate here the actual vapor pressure and This equation here you don't know yet here, but you have it now. This is a half empirical equation, and you have it in unit in kilogram per kilogram. Yeah, be cautious. This equation needs kilogram per kilogram for x, but our equation here for drawing the moisture rate curve is in gram per kilogram. Good, and by these gray equations we can calculate here our relative humidity of the drying air. And the K value is a function of temperature, X and phi. Good. Related to the green input fields. Now you see I have prepared 3 more, one where T is varied, one where X is varied, and one where phi, air velocity, is varied, keeping the others constant. Yeah? Still green, still default, but I can change here this value from 60, yeah, I could go up or down, and the same for the other red fields. Here for X and here for velocity. Okay, at the moment all 4 columns are on default. They are all the same, and I have here just one curve, one moisture ratio curve. So if we now go up, let's say for 10%, in all these red parameters, what do we expect? If we go up with temperature, what do we expect from this curve? How will it move? Temperature going up, maybe to 70. We'll go to the left. We'll be quicker, right? So if here the absolute humidity of the air will go up, what will happen? To the right. I would agree, would go to the right. If the air velocity here will go up by 10%, when air velocity will increase, I have a more intensive exchange of heat and mass flow. To the left. Ah, you're right, because I don't know. You're right, yes, to the left. No, you're right. Okay, we go to the left. So, and I prepared here this in the field as a factor. Yeah, here I have now factor 1, and now I can go up by 10% or 20. Yeah, I did this by this nice scroll bar here. We'll see if it happens with my touch board. Yeah, now we are here at 10%, and we don't see much change. At least we see that the temperature went to the left. Maybe I have to increase a bit. 20. Okay. Now we see a bit effect. Now I have increased here by 50%. We are here now at 90-degree drying temperature, and we have increased here the humidity to 15 instead of 10, and you see the variation of the humidity is not very much visible in this range. Yeah? But the air velocity shows a little bit effect here. And this shows us that the temperature here is the most important parameter. I go in the other direction. Okay, the same game, you see even more visible here when we go down with the temperature here, takes very long time, but the other parameters don't have such a big effect. The humidity only has effect when it comes to equilibrium. Yeah, when we come to 60%, and we are here far away from this. Okay, so you could start, but first let's have a look in the other spreadsheets, because the quicker ones can then move on in the other spreadsheets. So in this spreadsheet, we just are transferring the moisture ratio curves in moisture content curves. Here we have, on the very left, we have the moisture ratio. So, moisture ratio, it's the same as we have had here, moisture ratio, but then we are transferring this by this equation here to moisture content dry base first, and then to moisture content wet base. And then we have here on the right this nice chart to see it in real life, moisture content wet base and the effect of temperatures like that. Okay. And then the next spreadsheet. Here we are calculating here the time to reach target moisture content. And I can give you then, when we come there, more explanations. Let me find my see. I have to reduce the size. Okay. Here even the nice charts are prepared here, and always students are asking me, where are these lines coming from? Those, I call it pointer lines, they are in the gray fields. In the gray fields here I prepared here these lines which are pointing here to the things we need. Here, for example, from the blue sorption isotherm, we have to read the target moisture content. Okay, we know 0.6, going to the sorption isotherm for 20 degrees centigrade, and then going to the left to read here the moisture content at target. Okay, so we start slow and we go to the moisture ratio curve, and we try to fill in maybe here first relative humidity, and then K, and then here simple equation, the moisture ratio curve. Okay, ready to start?